Hi everybody, this is Binyamin, and I'm going to speak today about the physics of climate change. And the reason it says physics is because I'm a physicist. I am not a climate change scientist. Otherwise, I would have said the science of climate change. I'm trained as a engineering physics in engineering physics. There are other YouTubers that have an engineering physics degree, such as Derek Mueller from Veritasium. He actually learned in Queens, and I learned at a rival university in McMaster. But we had a nuclear power plant. That's why I went to McMaster. So I'm talking about the physics of climate change. I'm looking at it from a fresh pair of eyes, a skeptical pair of eyes, and I'm going to go through it as a physicist would. And the reason I say that is because that's how I go through the world. I look at the world as a physicist looks at the world. Every day I'm looking and observing and experiencing the world through the lens of physics. So that's why I say this. Now, first of all, there's a disclaimer. Regardless of the truth, regardless of what I decide or what you decide or what anybody decides about climate change, humanity should care for planet Earth, okay? No matter what, if climate change is real, if it's false, I don't care. Humanity must care for planet Earth. Humanity should protect planet Earth and all of its creatures, okay? If we see a creature is about to go extinct, like the polar bears, which is the big fuss that everyone's going into, or the panda bear or whatever, and they're blaming climate change on it, we need to protect these animals. Obviously, not in a way that will hurt them, because human interference often hurts their genome and their DNA. But we need to get involved if they're about to go extinct because of climate change. And no matter what, we should be striving for clean entropy increase. And the reason why I don't say energy is a misnomer. As a physicist, we don't like saying clean energy because it doesn't mean anything. Energy is energy. It's always there. It's always been there. It'll always be there. We're not creating energy. What you're doing is you're increasing the entropy of that energy. And so by increasing the entropy, you are creating work, and that's really what we care about. So we want a clean way to create work. Clean means no adverse byproducts. So renewable entropy sources, low entropy sources. So that's what we should be looking at. And we should be preparing for a hot planet cycle. Now, this isn't obvious yet. I'll talk about it more later. But if worse comes to worse, no matter what happens, if climate change is real, and if we decide climate change is real, we should be preparing for a hot planet cycle, because the planet cycle will get warm. We will get warmer. And this I will don't take this as a fact yet. I will go through it and I'll show you why we need to do this. But just take this as an aside for the time being. So here are some standard climate change graphs taken from climate science papers, from climate science websites. And you'll see right away that these graphs are all similar in one way or another. This graph goes back the furthest to 400,000 years ago, and it looks at CO2. Okay, so this is the first graph here. And as a physicist, we want to look at just the data. We want to look at the data and get an impression. What is the data telling us? Okay, and you see that the parts per million at the lowest are 180 about parts per million, and they go up. Historical highest CO2 level, this is a claim here, goes up to 300 parts per million. And now, whoa, we're almost at 400 parts per million. Actually, by today, we have passed 400 parts per million. And everyone was saying that's a very dangerous value. We've passed it, okay? So according to this graph, wow, carbon dioxide is shooting high, okay? And you can see, look, there's a standard frequency of fluctuation here. If you look at a Fourier graph, you could probably see what the frequency is of this fluctuation, and it looks like there's a correlation between these periods. So this 100,000 years about each period. Look at that, 100,000. Another one, 100,000. Pretty consistently, 100,000 years, approximately, that this period is coming. And then look, shooting up all of a sudden. So this is this looks like an anomaly in 1950, and it like 1950, maybe that would have been acceptable, but we've gone way higher. Okay, so this is the first glance. Wow, 400,000 years. That's a long time. Here, this graph here only goes back 2,000 years. And okay, we're looking at the temperature. Okay, these are all different temperatures across the world. The temperature average Temperature is very consistent across this time. And we have something called a little ice age. It does dip down a little bit, and then it goes up. Whoa, way higher, way higher. What's going on here? What is going on? Look how high this is. So we're saying, this graph is saying, look, the right value that we're supposed to be at is -4 fluctuation, and we've gone up to +4. That is 1 whole degree Celsius. That is huge. Look at that huge increase. We must be responsible. Okay, and let's go at these two graphs. These are similar in how far they go back. This goes back 10,000 years, and this is global temperature, and this goes back 20,000 years in Greenland only. Okay, and you see in Greenland, yeah, 10,000 years. It's been pretty consistent, and you see the same thing with the global temperature. It's been pretty consistent, and then there's this huge dip here, just prior to this 10,000 year mark, and you see it also here. Okay, and then before that it fluctuates, but this is what's going on here. Little ice age. Oh, look at that little ice age here that we saw here. Look at this little ice age. That is like such a small dip. Look how high we're shooting compared to that. Look at that. Okay, now the problem with these graphs is they only go back a few 100,000 years, a few thousand years in this case, 20,000 years. We need to look more because the Earth is 4 billion years old. We need to look if these are actual patterns because this is just such a small period of time to look at, okay? So we'll look at the next set of graphs, which are a little bit older, this next graph here. And I really like this graph because of how smooth it was. The only thing I didn't like was this degrees Celsius, so I had to convert a few things for you guys. So here, the 80 degree mark is about 26.666 repeating. The 50 degree mark is 10 degrees Celsius. So this is a 16 degrees, 17 degree spread here. And the spread actually between our last hottest period and our last coldest period is about 11 degrees, okay? So this goes back millions of years. So previously we went back a few thousand years, a few 100,000 years. That's nothing. Look how small 3 million years ago is. That is the actual lowest temperature ice age, and we've been increasing ever since. This is a fraction of this huge graph. Now, we don't have any of these little statistical noise values. We have a very smooth value here on this graph, which gets us to see the long-term picture of the Earth. I'm sorry, I'm a bit sick right now. Okay? So this goes back to about 2.4 billion years. It's not all of Earth's history, but it's about half. Sorry. So first thing you'll notice is that these dips occur once in 200,000 years, once in 150,000 years. But on a regular basis, these are called ice ages. Here, there may have been an ice age, but it didn't dip far enough. But so we are currently coming out of an ice age that was the coldest temperature since 350 million years ago. And we're just coming out of it. We are still colder than this almost ice age that should have occurred 200 million years ago. We're still colder. And I put a graph down here. This is also in millions of years. So this is 300 millions of years, 200, 100. So you see the dinosaurs went extinct less than 100 million years ago, around here, up here. Okay? This is how far back. So since the dinosaurs, the Earth has been getting colder, and now it's only starting to get warmer. And actually, it's been very stable, as you can see here, for 10,000 years, which is basically all of human history. Since humans have been on the planet, 10,000 years ago, maybe a little more, climate has been very stable. Okay, we have been very lucky. It has been very stable, and this blip here that's increasing is strange for us, for humans in human history. It's something that humans have never had to go through. Okay, we have, as long as we've existed, we have been at a stable temperature. Also here, more or less stable. So here is it's the same graph as this. You see that here, but added are the levels of carbon dioxide. Now you remember back here we were stressing out about getting to 400 ppm. Let's look what carbon dioxide did throughout history. Look at this. Look how low we are compared to all of human history. Look, there was this very low period here about 300 million years ago. 300 million years ago was here at the Carboniferous period. You see here the Cambrian explosion happened about 500 million years ago. You look, that is right here. Really, our carbon levels are the lowest it has ever been, except for maybe 300 million years ago. But for 300 million years, it's the lowest it's ever been. Okay, and our temperature is still below all of this period of 300 million years. We are at a very low point. Look how high it goes, 7,000 ppm. I mean, even below 1,000 ppm, we're freaking about 400. 1,000 ppm as a cutoff range, all of Earth's history has been above 1,000 ppm. So that's interesting. The other interesting thing is we see, look at this fluctuation that we've had of 11 degrees, and we're freaking out here about 1 degree. This could be statistical noise. This could just be statistical noise. We can't know for sure that it's a symbol that it'll keep going up, and it's because of carbon dioxide. And if you look at this graph and this graph, they're basically the same graph. This one just has the scale goes up quicker here on carbon dioxides, and the contrast is a bit better, so it's easier to look at, and there's also a little bit less noise. It's a little bit smoother to look at. But if you look at the general trend of carbon dioxide, okay, it's going down. This ice age had nothing to do, or maybe carbon dioxide went down. Okay, it could have caused an ice age. All right, maybe. But why did it get hotter after that? Carbon dioxide went down even further. So how did it get hotter after that? Okay, let's look. Carbon dioxide went up, and then directly after it went up, oh, it started getting colder a little bit and plateaued. Oh, carbon dioxide went really down. Okay, a little bit after that, the temperature dropped down. Oh, here's a correlation. Finally, there's a correlation. Okay, again, carbon dioxide goes up a little bit right here. Temperature shoots up. Like this goes up to 2,000 ppm. Temperature shoots up to where it should be anyways. And you get this little blip here. Maybe this contributed to a higher temperature. I don't know. And look here, this is the strange anomaly of a small ice age, an ice age that didn't quite go all the way down. And look, this carbon dioxide went up so high. Maybe that's the reason it didn't go down so high. I don't know, but this was natural. There were no humans in sight at this time. Okay? And then carbon dioxide drops really far, really far. And for a long period of time, there's no correlation here. It stays hot, and then it goes down. Okay? And we are at the lowest carbon dioxide and temperature levels, one of the lowest ones. And if you go back here to this climate change, you say highest historical carbon dioxide level is 300 parts per million? No, it's not. If you look at 400,000 years, it might be, but it's not. Highest is 7,000. 300 is down here. What are you talking about? 300 is like one of the lowest. Okay, so this is from just a data perspective. This is just data analysis. We should be expecting for temperature to go back up to 22 degrees Celsius average. We're freaking about 1 degree. It should look, if you look at the period of time that some of these ice ages last, it should happen. It should take about 2 million, 2 million, 3 million, 4 million years. Okay, it'll take a long time, but we will end up getting up higher. So we should be preparing for hotter temperatures globally, unless we're gonna try to nerf this temperature increase. But then we might also be exaggerating the temperature decrease that'll happen afterwards. So maybe we should start building underwater cities in California for 2 million years from now. We don't know. Everything might melt and the oceans might go over California, and we'd be happy that we built this underwater city. Okay? But we should be preparing for this. Now, what about the CO2 mechanism? Okay, so many people are saying, all of the papers are saying carbon dioxide is a greenhouse gas. It absorbs infrared energy. So let's just do a little recap here. This is our visible light. It goes from 400 nanometers up to 1,000 nanometer, which is a micrometer, up to here. And then we get into infrared. Infrared goes for about, it's from 10 to the minus 6 to 10 to the minus 4. It goes for a long time. Okay? So our infrared starts at this location here. Now, if we look here, we get 6.2 times 10 to the minus, sorry, this is a mistake here. Oh, that's why. Okay. Yeah, it was a mistake, and it was changed in the next slide by accident. Okay, this is actually more proper. Yes, so this is 1 micrometer, like it's supposed to be 10 to the minus 6 to 10 to the minus 4. Okay, I apologize for that mistake. You see here, it's 6, so it's actually quite far in the infrared spectrum where it starts. This is the black body radiation of Earth, okay? Black body radiation of Earth is in the infrared spectrum. The black body radiation of the sun is in the visible spectrum because it has more energy. And this arrow here is basically shows all the graphs follow the same direction in terms of energy. Energy increases as we move to the left, okay? So energy decreases in the visible light. And this is where all of the infrared, all of the heat signature of the Earth will be released. And this is the black body of the Earth. So we go up to 25 micrometers here. So it probably extends a little more, up to 50 micrometers maybe. And 6.2 micrometers is where it starts about maybe a little further. So if we were to look here, down here, I converted the values. The energy is still going up as we go this way. I converted the values a bit. So you see this 5 times 10 to the minus 6, that's over here. That's 6 times 10 to the minus 6, this 2,000. So this peak of absorption, so this is transmittance in carbon dioxide. So transmittance in carbon dioxide, from a physics perspective, it's very transmitted. There's a little peak here that's below our black body radiation, so this would not affect the Earth. But here, there's a peak here that's between 10 micrometers to 22 micrometers, which is here. Between 10 to 22 micrometers, there is something here. And this is what the graph here labels CO2, this little peak here. So this here is this peak here. If we were to increase the parts per million of carbon dioxide, this peak will go lower. And this is really the thermal energy that we are going to be holding on to in the Earth. This energy here. It might fluctuate a little bit lower down to here. So really, this is what's going on. I overlaid on this next slide. It went back to 10 to the, this is weird. Okay, this is the accurate slide, 10 to the minus 6. This goes back to 10 to the minus 3. It was a mistake. Ignore that, please. Here we have, so here I made it about the same level. The 6.2 is really just above the 5. This peak is lined up to here, and then it continues on. You can see here that this is the size here. There's no other, this is absorption rather than transmittance, but there's no other absorption peak here until the black body radiation will die off. There is an absorption peak here, but this is not where the Earth is radiating, okay? So even the mechanism that people are saying, this carbon dioxide as a greenhouse gas mechanism, is faulty. It'll only increase it by a little bit. This is such a small portion of the thermal radiation getting out of Earth. It's such a small portion, okay? This is just insane that people think carbon dioxide is going to be a greenhouse gas and cause warming in the Earth. Something else is causing warming, I agree, but this is not a mechanism according to physics, okay? So I'm not a climate scientist. Maybe I don't understand their science. Maybe I'm wrong. And this is what I need to say. It's okay to be wrong. I might be wrong. It's okay to be wrong in physics. I'm a physicist. I'm not here saying I'm 100% right, but this is my initial first principles analysis of the situation. I don't see that carbon dioxide is causing global warming or climate change, and I do see that climate change is a pattern and that it will return to about 24 degrees Celsius average in about maybe 10 million years or so, 3 to 10 million years, and that's just a guess. I'm not doing an actual Fourier analysis. I'm not doing a doctorate on this. I'm just looking at it from a basic perspective. So it's okay. And this is actually why physicists allow string theory to exist. String theory is could be wrong. There's no verifiable evidence of it anywhere, and people are investing their lives. They're emotionally invested in it. But no, they're not emotionally invested in it. String theorists will actually be happy if string theory is disproven. And they won't feel like they've wasted their life because it's part of physics. It's part of science to be wrong. Okay? And claiming that, oh, you're a string theory denier, string theory is the truth. No respectable physicist will say string theory is the absolute truth. The most they will say it's the best theory that we currently have. I would think that it's true, but it's not proven. We don't know that it's true, right? So same thing with climate change. How is climate change proven? I've just gone through it and I've looked and I don't understand. Maybe I'm missing something. I'm not a climate change scientist, but it's okay to be wrong in physics. I have no problem being wrong, but I part of the scientific process is looking at things from the other perspective, is doubting the results, seeing how things could be wrong, and maintaining a healthy degree of skepticism in all things is really what a proper scientist should strive for. And this is the healthy, proper science that that physicists are practicing in string theory. So it should also be this degree of skepticism should be present in climate change. But it's not okay to harm the Earth. Okay, so this is what we have to deal with. We don't want to harm the Earth. We still want to reduce our carbon emissions. We still want to make the Earth greener and a more environmentally friendly place for animals and for ourselves in the end. We shouldn't need climate change to scare us into doing the right thing. Okay, we should be doing the right thing no matter what. Okay, and may our legacy be truth. May whatever we find to be the truth remain. Like, I don't want a future generation to say, hey, look at all these idiots. They all believed in climate change and it was wrong. Well, no, we didn't. We were looking at things from a perspective, and we were looking at them and thinking, hey, climate change might be wrong, even from our period in history. So anyone who promotes science should promote a healthy degree of skepticism. And this is one of my favorite shows was Penn and Teller's Bullshit, and they're not scientists, but they did teach skepticism much better than any of the so-called scientists today who are calling people who disagree with climate change deniers, quote unquote deniers. And real scientists wouldn't start calling names like that. Wouldn't start saying, "Hey, you're a denier. You're ignorant." That's not what science is. Someone who is a true scientist would say, "Great, there are people who are questioning climate change. This is beautiful. This is the beauty of science. Let's investigate these queries. Let's see if they hold any truth to them." Okay, and we should be happy and gleeful at the idea that there's a different point of view. Okay, and this is really what any science educator should come to the table with. You know, climate change is the accepted consensus today through climate scientists. I'm not a climate scientist, I'm a physicist, and I don't see why climate change is so true, but maybe I am wrong. Okay, and I have no problem with being wrong. That is what any true scientist would say. Okay, conclusion, keep the earth clean. It's the responsibility of humanity. And keep science clean. That's the responsibility of scientists, okay? So don't start calling deniers who are part of the scientific method. Deniers are part of the scientific method. All of the biggest breakthroughs in science came because, I'm not saying I'm a genius, but some person doubted the status quo, doubted what everyone accepted to be true, okay? So that's the responsibility of scientists, to have self-doubt in everything, okay? And we should be preparing for a hot planet cycle, like I said before. If you look at the data, as a physicist, I'm saying this is going to go up to 22. We should be prepared for this. The other thing, as a physicist now, I understand this is a doctorate thesis type question. It's not a simple question to answer, but because of the fact that carbon dioxide doesn't appear to be what's it called? Correlated to climate, because it doesn't appear to be, maybe something else is causing it, right? And we saw that this 1 degree here, we see 1 degree fluctuation is just common in history. Look, all of this is 1 degree fluctuations. Okay, all of this is 1 degree fluctuations. This could be just natural statistics. But if we really wanted to know, we should be examining this other point that I have here. And this further question is, what about the temperature increase? What should we expect as a temperature increase based on our technological entropy increase? Now, normally people would say energy use based on our energy use, but that's a misnomer because we're not using energy. We are increasing the entropy of said energy, okay? So because of this increase in entropy, we should be able to measure what the overall temperature increase should be in the world. And what's interesting is this has nothing to do with carbon dioxide emission. This will work. Sorry, this will work with nuclear power, and this will work with sun and renewable energy. We are increasing the entropy around us at an accelerated rate. That is what energy use, quote unquote, is. We are increasing entropy. And this should be always accompanied by an increase in enthalpy. Not always, but in most processes, and especially in the way that we use energy, enthalpy will be increased. The amount of heat in the earth will increase. Does that correlate? Maybe that has more of a correlation, because I don't see the correlation in CO2. I hope you enjoyed this. I hope it gave you a little bit of healthy skepticism in climate change. I'm not saying that climate science is wrong, but I'm saying from a first principles new perspective, when first investigating this as a physicist, I don't see it. I don't see how climate change is correct, okay? These questions have to be answered in order for climate change science to proceed. In my perspective, I have to see them answered somewhere. And I've looked at journals, and I've looked at papers, and I've looked at websites, and nobody addresses these problems. They don't even bring them up. And this is really just the type of things that you, just from being a physicist and looking at it the first time, this is how I analyze the problem, and it doesn't line up. I don't see it. I don't see it line up. And it's not, I'm not looking for ways to doubt climate change. Like, this wasn't what I was going out to do when I started investigating it. I just wanted to understand it from a physics perspective, and I went through it as I would go through anything. And the data could have been different, and I could have completely accepted climate change. But because the data is the way it is, this is the process that I went through, and that I think any physicist would immediately go through. Well, let's look at the transmittance of carbon dioxide right away from these graphs. These are graphs that I've seen all the time throughout my education. Let's look at the data and look if there are any trend patterns over longer periods of time, because these are very short periods of time statistically for Earth history. And Earth as we know it only evolved over the past 3 million years. Most of the life that we are currently aware of and see, like all bears and primates and just us, is 10,000 years. We've been in a steady climate change, so a steady climate for that time. So this is rare and strange for us, but for the Earth on whole, it doesn't appear to be strange. So I hope you enjoyed it. I hope you stop calling people that are going against climate change as deniers, and respect them as the healthy skeptics that we need in science for all things. Okay? Part of the process of learning is doubting what you've been told. Okay? Part of the process of a new generation, part of the process of any advancement is doubting the status quo, and this is healthy in humanity. Okay? So please applaud them, but don't call them deniers. And no matter what, even us deniers, if I'm a denier, I don't know what I am, I don't categorize myself as a denier, we should all agree that no matter what, the end result is the same. We should be making the Earth a better place. We should be being more environmentally friendly towards the Earth, even if we are not causing climate change. We shouldn't need a scare like climate change to be doing what we're supposed to be doing anyways. Okay? Thank you very much for watching, and I'll see you next time. Bye.